Welcome back. We are in the middle of proving this theorem about Galois extensions. We are trying to show that an extension is Galois if and only if it is the splitting field of a separable polynomial. And as I told you last time, this is a very convenient way of verifying if a given extension is Galois or not. And we proved in the last video one direction of this. So we assume that K over F is Galois. And using some pretty involved arguments, but still not very difficult but lengthy arguments, we showed that K is indeed the splitting field of a separable polynomial. And in fact, in the process, we really showed that a Galois extension is always normal and always separable. So now in this video, we are going to prove the converse. So I am going to assume that K is the splitting field of a separable polynomial. K is the splitting field of a separable polynomial in capital Fx. Let's call that polynomial f, and it is of course splitting field over capital F. So what we have is K and F, and F is a polynomial in the base field and K is the splitting field. So we want to show that K over F is Galois. In other words, the definition of Galois extensions is that to show F is equal to K power Galois K over F. Okay, so we always know that K power Galois K over F is an intermediate field for the given extension, and our goal is to show this. We want to show equality of this. Okay, so and we are going to induct on a strange number. So let me explain that. So first we note that of course F splits completely in K. So which is to say that F can be written as a product of linear polynomials in Kx. So all the roots of F are in K. But we are going to induct on this number, which I will denote by n. It is the number of roots of f in K minus f. Okay, so as I said, this is a strange number to induct on, but this is what we will do. And to just motivate what this number is and to do also the base case, let's take n to be non-negative, n to be 0. So n of course is a non-negative integer, so because it's a number of roots. So if n is 0, then there are no roots of f in K minus f, because number of roots of f in K minus f is n, and that is 0. But that is to say all the roots of f are in F. Remember that all the roots of F are in are in K for sure, because K is the splitting field. But if none of them are in K minus F, that means they are all in F. So F splits completely in Fx itself, because if it splits completely, if it is all the roots, then it splits completely. So K must be equal to F, right? Because K is the splitting field of the polynomial, and if the polynomial splits completely over the base field, splitting field is the base field. And obviously this, I am not sure I said this explicitly before, but this extension is Galois. An extension, trivial extension is always Galois, because the Galois group is the identity group, the fixed field is that. So various ways of verifying this. The degree is 1, the Galois group cardinality is also 1. Okay, so assume now n is positive, and I am now going to explicitly write down what the induction hypothesis is. The induction hypothesis is the following. What is the induction hypothesis? It says the following. So, given any intermediate field L, so that means we have K, F, K over F is the given extension, L is an intermediate field such that F has fewer than n roots. In K minus L, we have K over L is Galois. Okay, so this is the induction hypothesis. Remember that the original hypothesis is K over F is the splitting field of a separable polynomial, namely F. That hypothesis also holds for K over L because F is in Fx, which is of course in Lx. So F is a polynomial over L and K will of course remain splitting field of F over L also. And if it happens that the number of roots in K of F that are not in L is fewer than n, that means strictly less than n, then that is Galois. So that we will assume. Okay, now to proceed with the proof, let F equal to F1 times F2 times Fs be the irreducible factorization of small f in Fx. We are given this polynomial f, it may very well not be irreducible, so we can take its factorization, irreducible factorization. Remember, this is in Fx. Since n is positive, that means f does not split completely in f, at least one fi has degree strictly more than 1. Because if each fi is degree 1, that means f splits into a product of linear polynomials, which is to say f splits completely, which means n equal to 0. So now we are assuming n is not 0, so that means fi is at least one fi has positive degree. So we might as well assume without loss of generality that f1 has degree r, which is strictly more than 1. Okay, now I am going to take, let alpha 1 in K be a root of f1 in K, so that means alpha 1 is in K. Remember that f splits completely in K, that means f splits completely means f1 also splits completely. So it has all the roots in K. I take just one of them, alpha 1, and now I am interested in this intermediate field. Now I want to note the following. The number of roots of f1 or f rather in K minus f alpha 1. Remember, alpha 1 is not here. That is because f1 is irreducible. So I will just remark that here. f1 is irreducible in fx. This implies f1 has no roots in f, because if it has a root then it cannot be reducible and its degree is positive. That is important, because the only way that it will have a root and fail to be and it is irreducible is degree 1. So if it has degree greater than 1 and has no roots, then if it is irreducible and degree greater than 1, then it has no roots. So in particular alpha 1 is not in f, right? So now the number of roots of f in K minus f alpha 1 is strictly less than number of roots of f in K minus f, right? This is clear because alpha 1 contributes to this number, because alpha 1 is a root that's not in f, but alpha 1 is in f alpha 1, so alpha 1 doesn't contribute here, right? So alpha 1 is in f alpha 1, so it's not in K minus f alpha 1. So the number of root and every other root will remain the same. So number of roots of f in K minus f alpha 1 strictly less than, because at least one less. Maybe there are others also that are in f alpha 1, but we don't care. So it is strictly less. So induction hypothesis applies to F alpha 1, and we conclude and K of alpha 1 is Galois, right? Very good. So this is Galois by induction hypothesis. So that is going to be crucial to us. In particular, hence, so spelling out the meaning of being Galois, K power Galois K over F alpha 1 is F alpha 1. So we will use this in a minute. So now what we do know is F is separable. This is hypothesis. This of course implies that F1 is separable. This is just definition, right? If you have a separable polynomial, all its factors are separable. This means, and degree F1 is of course R. So F1 has R distinct roots in K. Because F1 splits completely, all its roots are in K. So because it is separable, there are R of them, say alpha 1, alpha 2 up to alpha R. Alpha 1 is something that we have already chosen, right? Alpha 1 is chosen here. So alpha 1 was chosen here. The remaining roots are called alpha 2, alpha 3 up to alpha R. Now I am going to construct some elements of Galois K over F as follows. And this one is just a direct application of extension theorem. So I will go fast over this. So you have a map from F alpha 1 to F alpha I, right? So these are both extensions of F. This is simply because this is Fx. I mean, this is triviality, right? This is isomorphic to Fx mod F1, and so is this. Here the point is alpha 1 goes to alpha I. So this is true for all I equal to 1 to R. Remember that we have R of them, R alpha I's. So there is an F homomorphism from F alpha 1 to F alpha I, sending alpha 1 to alpha I, and of course K are extensions of this. And using extension theorems, we can extend sigma, this map to sigma I. So sigma I is a function from K to K, automorphism which fixes F, so which is to say which fixes F. So that means this is because this is an F extension map. So here F goes to, every element of F goes to itself, alpha 1 goes to alpha I. So when you extend it, it will continue to fix capital F. So that means by definition these are F automorphisms of K. So that means they are in the Galois group. And second point is sigma I of alpha 1 is alpha I, and this is true for all I equal to 1 to R. So that means we have R constructed automorphisms of K now, F automorphisms of K, and which send alpha 1 to alpha I. Okay, so far so good. Now I am going to claim the conclusion that we want to prove and prove it. So we show, so basically K of is Galois, that is K power Galois K over F is F, right? So that is our thing to prove, and the proof is as follows. So remember clearly, this is something that I mentioned a little earlier in the video. F is certainly contained in the fixed field because here all the elements are F automorphisms. So we only have to show the other inclusion. Meaning K power Galois K over F is in F. So now let us take a beta in this. Let us take a beta in the Galois group, and I am going to argue very soon that beta is in fact in F. So that's the goal. Beta is in F. So now the first point I want to argue is, so this is an exercise, maybe I'll write a bit more and then write the exercise. So every element of Galois K over F fixes beta by definition, right? Because beta is in the fixed field of Galois K over F. Now where are we? So we have the picture that I had earlier. I will rewrite it. K contains K contains F alpha 1, which is an extension of F. Okay, so this is simply because beta is in K power Galois K over F. So that implies every element of Galois K over F fixes beta. But now what is the relation between Galois K over F and Galois K over F alpha 1? Just think about it. This in fact came up in a problem session earlier. So what is an element of the left hand side here? It means it's an F automorphism of K. That means it's an automorphism of K that fixes every point of F. And what are elements here? This is an F alpha 1 automorphism of K. That means it's a K automorphism that fixes every element of F alpha 1. But if it fixes every element of F alpha 1, it certainly fixes every element of F. So this is what we have. So this is a simple statement. Every element of every automorphism of K which fixes everything in F alpha 1 is a K automorphism which fixes everything in F. So this is an automorphism of K which fixes everything in F. So this is a triviality. Now I claim, let's look at the fixed field of these. So now these are things that are fixed by every automorphism of K. These are the things fixed in K by every F automorphism of K. These are things in K that are fixed by every F alpha 1 automorphism of K. So now because this is a smaller group, if a bigger group, every element in a bigger group fixes an element, it is automatically fixed by everything in a smaller group. Okay, so this is the exercise that I want to give. It's a triviality. Let K be a field and let H in K be two groups of automorphisms of K, H in G. So that means K is a group of automorphisms and H is a subgroup. So then K power H contains K power G. This is a triviality because everything in G fixes something here. So that means that element is fixed by everything in G, but if it is fixed by everything in G, it is fixed automatically by everything in H. So it is in fixed field of H. Okay, but now coming back to the proof, beta was chosen to be here, right? Beta was chosen to be here. So that means beta is in K power Galois K over F alpha 1. But now induction hypothesis told us what? All the way back I wrote here. This is the induction hypothesis, right? K power Galois K over F alpha 1 is F alpha 1. So that means this is equal to F alpha 1. So beta is in F alpha 1. So hence beta is in F alpha 1. But now another exercise for you. If K over F is some algebraic extension and alpha is here, let's say degree of alpha is R, then an F basis of F alpha over F is given by, F alpha is a vector space over capital F and a basis is given by 1 alpha alpha square up to alpha power r minus 1. This is because to begin with every element of F bracket alpha is a polynomial in alpha. So in general it will require all powers of alpha, but because degree is r, any power alpha r plus 1, alpha power r plus 2 and so on can be expressed in terms of these using the polynomial which has alpha as a root. So applying this exercise, we know that an F basis of F alpha 1 is 1 alpha 1 square up to alpha 1 power r minus 1. So, write beta is equal to A r minus 1 alpha r minus 1, A r minus 2 alpha r minus 2, A1 alpha A0, where of course the point is AIs are in F. So, it can be represented by an F linear combination of these elements. It is in fact a unique expression, and this is what I have done. Okay, now let us apply. So, recall the automorphisms that we constructed, sigma i's. These are elements of the Galois group, right, of K over F. And what are the properties of the sigma i's? They send alpha 1 to alpha I. So, let us apply sigma 1 up to sigma r to this equality, this equation. So, what do I get? Because beta is fixed by the Galois group by hypothesis and sigma is r in the Galois group. So, beta will be fixed by sigma. So, this is beta. So, I am going to take 1 less than I less than equal to r. This is going to be, because AIs are also in F, sigma is going to fix that also. So, I am going to simply write this as sigma I alpha r minus 1 r minus 2 sigma I alpha r minus 2 plus dot 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 A1 sigma I alpha plus sigma A0, because sigma I fixes it. Okay. So, this is what we have. So, we have in fact r equations. For every I from 1 to r, we have these equations. Now, the last step, we are almost done. Let us consider the polynomial hx to be a r minus 1 x power r minus 1, a r minus 2 x power r minus 2, a1 x plus a0, but I will subtract beta from this. So, this is a polynomial in f alpha 1 bracket x. Remember that this is a priori not in fx, because while ar minus 1, ar minus 2, a1, a0 are in f, beta is at this point only in f alpha 1. We will show that it is in f, but we are not yet there. So, beta is in f alpha 1. So, this is a polynomial in f alpha 1 bracket x. So, degree of, so clearly degree of h is r minus 1, right, because ar minus 1 is certainly non-zero, or degree is at most r minus 1, let us say. Okay. So, then, but alpha 1, alpha 2, alpha r are all roots of hx in K. So, they are in K. Why are they roots of this? Because if you take h of alpha I, you get ar minus 1, alpha r minus 1, alpha I r minus 1, ar minus 2, alpha I r minus 2, a1 alpha I plus a0 minus beta. But now let us see what is on our screens. Alpha I is actually nothing but sigma I of alpha. Alpha I is sigma I of alpha. So, let us compare star and double star. So, compare star here and double star. I claim that they are exactly the same equations, because ar minus 1, ar minus 1, sigma I alpha power r minus 1, but sigma I alpha is alpha I. So, alpha I power r minus 1. Sigma I alpha is alpha I power r minus 2. A1 alpha I plus A0, star is written as this is equal to beta. So, this is equal to beta by star, right. So, that means we have beta minus beta. So, that is 0, and hence H has at least r roots, namely alpha 1, alpha 2 up to alpha r. And it is very important for us here that alpha 1, alpha 2 up to alpha r are all distinct, because otherwise we can't say then it has at least r roots, and that is the point here. So it's crucial that alpha 1, alpha 2 up to alpha r are distinct, and this is where separability comes into play. So these are r different elements, they are all roots of H. So H has degree r minus 1, but H has at least r roots. But this is a problem, right? Because our field, a polynomial, can have at most as many roots as its degree. Here you have a degree r minus 1 or less polynomial, but it has at least r roots. The only resolution of this problem is H is 0. But if H is 0, each coefficient is 0. A polynomial is 0 means all coefficients are 0. So a0 minus beta is 0. That means beta is equal to a0, which is an f. Right? So beta is in f as we wanted to show. So this is a very nice, clever proof, and it shows that it's quite long, so we may have lost track of time here, but it shows that if you have a extension which is the splitting field of a separable polynomial, then it is Galois. Okay, so this proof is several pages long. In the previous video we proved one direction, and in this video we proved that if you have K is a splitting field of a separable polynomial over a base field f, then it is a Galois extension. So let me stop this video here. I wanted to derive some corollaries of this, but we will postpone that to next video because this is already a lot of material to cover in a single video. So let me stop this video here and we continue with consequences of this theorem in the next video. Thank you.